Hello, everyone. My name is Jimmy, and welcome to this week AI workshop. Hope everyone have a great weekend. And this week, our topic is to teach AI to see. In a less fancy word, is to see how we can use state-of-art model or modify them to solve and complete complicated image processing tasks. All right, let's go. So first of all, we need to know what image is before processing. Some people may think that image is one non-divisible thing, like you just have one image and that's it. But if you zoom in the picture big enough, you will actually see it consists of many pixels. You can see the example over here. For example, imagine this is a size 50 times 30 image. That is like, it's the 50 is the width and 30 is the height. If we zoom in big enough, we will find out it actually consists of 150 pixels. If it's, for example, like this, it's like a 2D array, a nested array. Since this is a colored image, you can have multiple color channel, but just remember, this image is actually an image array, pixel array, with the pixel value range from 0 to 255, 0 taken as black, while 255 taken as white. This is the important part you have to remember. Everyone understand? All right, so before we talk about the CNN, I hope you guys heard about convolutional neural network before. But if you never heard about it, it's fine. We'll go over the detail today. So, but before I talk about convolutional neural network, I do want to emphasize a little bit about artificial neural network on image tasks. People have done this before. They try to train a deep neural network like this kind of a model to solve image task. But it doesn't really work. Why? Let's see. So how they do is basically flatten the pixel array out. Imagine the last slides that I said, if you zoom in the picture enough, it actually consists of many pixels. People, what you do is basically flatten the whole pixel array out. So no matter it's either a 2D or 3D array, if it has multiple color channel like red, green, blue, it becomes a 1D array like this. And each pixel value becomes input node. Do you understand? Like each, for example, if the pixel value is like 255, it's a white, then you just enter here. Can you guys think about some problem with this kind of model? So basically, I will show you the answer. The limitation of artificial neural network, first of all, is the huge parameter even with small sample size. Imagine a 50 times 50 color image. It's really small in modern day size. If you look at a random image, you will see at least have like 1,000 times like 1,000 image size. So this is a really small image. But even with this really small color image, if we flatten everything out, the first layer will have 7,500 nodes. With the second layer, at least 5,100 nodes, because that's the least we need in order to trainable. You have 37 million parameters. So let's go back to see here. See how many parameters we have? Parameter is basically weight. See, the first layer has 4 input nodes, and the second layer has 5. It has 20 different connections, and each connection is going to have a weight. So if we use the same math here, a simple 50 times 50 color image, the first layer going to have 37 million parameters. So it's definitely not good, right? Think about it. That's a lot of parameters. That means we need to have really we need to use a lot of computer memory and storage room to either store them and compute them. And also, one of the properties of image is pixel and pixel are correlated. Take an example of this image. As you can see, what makes this a mountain? It's not just one pixel like fire up, or one pixel that is black. It's multiple pixels that like it's like they correlate to each other. Like if those pixels fire up each other, you can see this like a boundary that shows the mountain. But if we flatten the node out, you just lost, the correlation is lost. we may be able to train the model to recognize this pattern in the future, but basically we just lost this correlation in the beginning. So that's not really good. So can we find out a model and take advantage of this property and make our model better, faster, and smaller? And this is where convolutional neural network comes from. Convolutional neural network is one of the most famous, popular model in image processing tasks. So if you take a look at this, what's convolutional neural network, shortened for CNN, is it's basically have an input image. You have a convolutional layer, a pooling layer, and then multiple convolution layer again, pooling layer, and then with the fully connected layer. You may not understand every single layer, what it means right now, but I'll explain to you in the future. Let me see. But basically the idea is, unlike the vanilla deep neural network model, where you basically flatten everything out, the convolution layer take advantage where in an image, pixel and pixel are correlated. This is where we need kernels. Kernel is one of the most important feature in the convolution layer. I hope you guys can see this image. This is a kind of simplified version of what a convolution layer does. Imagine in the first slide that says the image consists of image pixel. Just imagine this is also an image, a size like this image, and each one is basically a pixel intensity value. For example, 105, 102, or 100. What kernel does is basically project each feature and extract the feature out. In the next slides, I will show you more about it. This is what convolution kernel operator is. Imagine you have a picture like this, where 10 is basically considered as white, while 0 considered as black. As you can see, if we kind of make this as an image, it will look like this, where white is over here and darker color is over here. We can clearly see there's a boundary that's separating these two regions. And what kernel does, as I see over here, is basically act as a feature extractor. This is really important. It acts as a feature extractor. For example, and there can be different kind of feature extractor. As you can see here, it's horizontal line feature extractor, vertical line feature extractor, 45-degree feature extractor. But how does it actually do the work? I'll show right here. And as we can see, this is a vertical line feature extractor. What it does is basically, it's like an operation. First of all, how it works is basically you multiply each value. For example, over here, 1 times 10, 0 times 10, negative 1 times 10. You basically multiply each value with the corresponding value in the input image. And the value you will get is this. How it does is basically you slice through the kernel to the image. Each time you basically calculate the value over here. You basically calculate, you multiply each value with this, multiply the value with this, multiply value with this. You add them up, and in the end, you put the value into the center of this. That's why you see the size becomes smaller when you basically finish the kernel operation, when you slice through the whole image. And as you can see, with this feature extractor, we can clearly see the kernel actually find out there is a bound, it's a border here. As you can see, this like values 30, 30 over here and 0, right? That means there is a, and we can see, we can verify this. There is a border over here, and we can find out there's a border over here. So do you guys still have any question about kernel? It may sound confusing at first, but like that's just a simplified version of the kernel. If you're really interested, you can basically look online. There's more material that go deeper for this operation. But to remember, the most important part is basically kernel is act as a feature extractor. And for each convolution layer, there's many, many kernels. They can be 100, they can be 1,000, but usually it's like 20 or 30. And we don't specify any kernel. So we don't specify like we have to find this feature or that. It's all done using machine learning. So machine find out what's the best feature that, like most common feature that I can extract to basically get the best prediction outcome. And the pooling layer is basically, most of the time, as you can see in these examples, the size of the image goes down when each operation, each kernel operation that you slice through a whole window. But most people doesn't do that. They use like padding. It's basically adding an extra 0 around the border. So if we do the same operation of the kernel operation, the image size is going to still the same, still be 6 by 6 after the operation. But yeah, because then we can have multiple convolution layer. Because in a modern day state of our model, like you need to have at least like 20 convolution layer, like 15 to 20 convolution layer. So if we decrease the size by that too fast, it's not going to work. So most people using padding, they try to keep the size stable the first, and then they have a pooling layer. Is basically decrease the size of the feature map. Feature map is basically the output after the kernel operation, because we extract the feature, right? So do you guys have any question? Okay, so so basically each kernel act like a feature extractor, and the pooling layer goes to decrease the image size. But what's some limitation of vanilla CNN? Let's go next slide. The output is not really useful, right, in the real world, because imagine you're a machine learning scientist. Most of the time, we just don't take a picture and ask, what's the picture about? Sometimes we want to know that where is, like for example, if we want to take a picture to classify human, we don't really, besides knowing if the picture contains a human or not, or it's like a dog, maybe we also want to know where is the human. Is the human in the top right of the image, in the center of the image? Is human like cover 80% of the image, like the whole picture is about the human, or it's only contain a really small part of human? So human is really small. We also want to know the location of the human in the image, right? And another problem is a little bonus. It's like the image size has to be fixed, because as you can see the model over here, since we have a fully connected layer, that means we have to flatten it out and have like each going to have we basically flatten the feature map out and do the artificial neural network again. So basically it's the same thing like this, but instead of running on the input image, we actually run this on the feature map. So we need to have a fixed image size, because everything here is basically fixed. So we need to have a fixed image size. So for example, if we change the CNN model with the image size 50 times 50, and the CNN is only going to be useful for the 50 times 50 image. For the other image size, it's not going to work. We have to do some pre-processing. So it's not really useful, but it's just the bonus part. So now, can we improve it? And I will start with a case study, because case study usually works best and help you understand anything better. Imagine we're programming a self-driving car. What's the first thing we can improve from the CNN? It's localization, just as I said before, right? Because for vanilla CNN, the traditional CNN, we only output a probability of if the image is a car or not in this given task. So next thing we can improve is localization. And this is localization with simple image examples. So we have a cat. If we just classification, it is a classification output cat. But if it's a classification plus localization, besides outputting what the class label is, we also output a bounding box. Usually we just have an X, Y location in this point and the width and height, because the rest of them we can use to calculate. Some people may think, do we need to do some actual work about the model, like have some complicated model, like matrix multiplication? Actually, it's not. Remember what we output here as a probability score? It's actually really simple. You just add 4 more value. You just add 4 more output, a regression output about the coordinates and the size. It's that easy. But the only thing you gotta change is the error function, because when we train the probability, when we output probability, usually we use softmax as a error function. We basically maximize the softmax. But for the regression, usually we use least square. But that's some advanced stuff. But basically, just know that the only thing we have to do is just add some other error function to basically we can help to improve our other for localization output. It's really trainable as long as we have a separate error function, as I can see over here. And I will show you some examples of object localization. This is a website. I will paste on the chat. You guys should basically go on there and play around with it. I will do it too. If let me see the chat. Let me open the chat. Can you guys go see the chat? Can you guys see the chat? Everything good? So as you can see over here, it's basically a post estimation. As do you remember before that we also want to localize the object? This is a similar kind of task. Not exactly the same because this, instead of outputting, this basically only output localization instead of what the class is. As you can see, if I stay here, the machine learning task correctly classify where our eyes is, our nose. What is that? It's in, yeah. Sometimes it has some errors, but like since this is because since most people who run this on a browser, since we don't have GPU, CPU, it's sometimes the accuracy is not the best. This is the only post that basically estimated post. If you stand up, right now it's a little too close to me, so it doesn't really see my whole shape. But if I stand up, as you can see over here, you can see my whole shape over here. It's kind of cool, right? That's localization. I will show you right now. If you go on their GitHub page, that's not the most crazy part. When we do the object detection, it's better. It's better. As you can see over here, this is the postnet. We can see its output. Its output is basically X, Y, and score. So as I say before, we can just output all kinds of things. We can basically output a location instead of besides the classification. And that's what it does. It's basically outputting X, Y position and the score. Okay, understand? Everything good? Okay, so you can definitely play around with this after the workshop. This is blocking. And there's a lot of parameters you can also tune, like as I'll show you right here. As you can see over here, this is an important part you need to pay attention to. Architecture, this is a mobile net and ResNet. The only difference is that, do you remember that I said before that like the accuracy of this is not really good? Because we're running on a mobile net, which is a less accurate net, but it's like smaller and faster. So if you want a better accuracy, you can choose to use ResNet. ResNet is a larger but more accurate model. But like, yeah, just a note. Okay, so after the example, what's next? Now our CNN becomes better. What's the next thing we can improve from the above CNN? It's the object detection. Since most likely, imagine you're a machine learning scientist, you want to program a self-driving car and you get input from the car camera. Since there'll most likely be more than one car or one pedestrian in the input image, right? Because we don't really take image. So there's gonna be more than one car most likely if we output in the market. So that's the difference between object detection and object localization. See this image? Image classification is a cat. Classification with localization is basically a car and it's a bounding box. Detection, that means we need to basically detect multiple objects in the image. See, there can be more than one object we need to identify in the image. We need to output the correct bounding box classification for each object in the image. And think about it. Why can't we use the traditional CNN architecture anymore? Before I say for localization, we can just add an actual output that output coordinates. But why can't we do the same thing with this anymore? Think about it for a couple of seconds. And yeah. So the vanilla architecture of CNN, the base CNN, is not applicable in this task anymore because the architecture of CNN requires a fixed amount of object output, right? Imagine here. Or even we ask for coordinates, it's fixed. If the object detection object amount is not fixed, there can be like one object or no object. So, well now, it seems like a complicated task, right? Because we cannot have a fixed output anymore. So we need to think about something new and creative. This is where RCNN comes from. It is a little difficult complicated to understand, but no worry. Just try your best, all right? You basically passing a region proposal network. It's basically when you put an image, we will do some fixed computing. Because before machine learning even existed, humans have been spending time to trying to find ways to do image processing before machine learning even come to existence. So they use those kind of fixed traditional non-learnable algorithm to basically extract different region. And when they extract different region, they basically put them together and then basically compute the CNN feature. It sounds a little complicated, but just remember, we have a feature, we have a region output, region proposal network, because they can be different objects in the image, right? So now we have to do is basically use an algorithm to basically propose a bunch of regions that we think have a high probability having the object. And then we basically passing into the CNN, the convolutional network, I said above, with the region. So we extract the region out that we think has high probability having a object in there, and then we put a high probability region into the CNN, and then the CNN going to output a score of what is there actual object in the image. If it is, what is it? And also the corrected bounding box coordinates. Okay, so what's the problem about this? It takes a huge amount of time to train and use, and each region proposal run, and for each region proposal, some people, most likely people like to use like 2,000 region to reach have a good accuracy. So imagine you running a CN with 2,000 region. That is waste a lot of computing resources and time because a lot of regions are actually overlapped. So basically you run CNN on a lot of overlapping. You basically have a lot of overlapping wasteful computation. It needs 47 seconds for testing image. So it's not even in training. Imagine you just passing an image and you want to get an output, it takes 47 seconds to get a response back. And the selective search algorithm is not learned. Thus, it can lead to some bad region proposal. I will mention this later. But just remember that for each region proposal, we have to run a CNN. And that is a big problem. So that's where fast RCNN comes from. Fast RCNN just make a little simple change of RCNN. Instead of doing region proposal network first and then put them into CNN, we input the image first and then do the region proposal. I will show you. So right now for this one, we have an input image, right? We extract region proposal first and then CNN. But for fast RCNN, is we input the image, have an input image, we basically run one CNN only one CNN. So we basically get a feature map. Remember, like after one iteration of CNN with different layers, you get a feature map of the image. And we do the region proposal on the feature map. So what makes it better than the RCNN? Because we only run with one CNN, that means we save a lot of overuse computing resources, because we don't really over calculate, like we don't really calculate the pixel multiple times running different CNN. Instead only run once. So it become way faster. And this is the training time and test time. As you can see, for RCNN, it's basically 49 seconds. For the fast RCNN, it's only 2.3 seconds. That's a really, really huge improvement. So it's really good already, right? But as we can see over here, the blue one is basically including region proposal and the excluding region proposal network. That's what people use to test the time. So we can see from this, with the including region proposal network, the fast RCNN run 2.3 seconds. Excluding the region proposal network run 0.32 seconds. So most of the time, it's a waste on the region proposal network. So now, people start to think, can we improve the region proposal algorithm time? Because this takes 2.3 seconds and it's a long time. And especially since the algorithm we use as the region proposal is fixed, it's not learned. So people start to think, can we like train a model to do those kind of tasks? And that's where faster RCNN comes from. It's basically learn a region proposal network. The detailed region proposal network can be a little complicated, but it's basically the same sliding window using convolution, but instead you will have some anchor boxes. But just remember, now we have a machine learning, like we use machine learning to train the region proposal network, so improve the speed by a lot. So as you can see, we have an image, we put them into convolution layer, we get out a feature map after the convolution layer, and then we basically do a region proposal network, and then we combine them into a classification with the ROI pooling. So basically, everything now is learned. So nothing is fixed. Imagine before the RCNN, we first have, let's go back to this image. The extract region proposal is not learned, and we run CNN with each region proposal. The faster RCNN basically improve everything it has, the problem here has. Basically has only one CNN run, so you save a lot of computation time. You also learn the region proposal network, so you can be like really good. So see the problem over here for the RCNN, the selective search algorithm is not learned, and it can lead to some bad region proposal. But because it's learned, it becomes better and faster, and that's where faster RCNN is. It actually improves the speed by a lot. I think it becomes 0.5 seconds for the whole run. So like, oh, actually 0.2 seconds. So it's become way better. So since everything's learned right now, but people still want to improve because people never like stop improving, right? So machine learning scientists start to think, can we do better? Can we improve the speed even more? If you pay attention to machine learning, you know that one of the most famous trade-offs between machine learning is speed and accuracy. So if you want to have a really good speed, sometimes we have to trade off with some accuracy. Just the same as the example I showed you before, that we have two different models to use, the ResNet and MobileNet. MobileNet is fast, but it's less accurate, and the ResNet is slower, but it's more accurate. So right now people can start to think, can we basically sacrifice some accuracy but reach a faster time? This is where YOLO comes from. YOLO, you only look once. Now you only live once, but you only look once. It's exactly as what it sounds like. Remember before that we have to have those region proposal network after we CNN? You basically stop doing that. What you do is basically take an image. It's split into like some fixed size. For example, you can split to 10 or 20 equal size. And on each box, you split into different small region, like fixed same size region. And with the, for example, you like for this image, you split into 9 equal size. And each one gonna have an anchor box. What is the anchor box? Anchor box is basically a thing that we predefine to use to basically calculate, help us to find out if there's an object in the anchor box is basically a thing we use to help us to identify if there is an object that we want in the region that we just split on. The output may seem a little complicated, but it basically has a probability of if there's a task, if there's an object here or not, and its location, and what object is it. Why anchor box works better? Because anchor box is a lot of anchor box works because it helps us determine the object. It helps us to basically, sorry, this may sound a little confusing, but anchor box works because anchor box works because it predefines the shape of the thing. So basically, you look for matching. For example, like just for example, for this this split region, it has two anchor box. If we have, for example, the people and the cars overlap, right? If we don't have this anchor box, it will be hard for machine learning to actually like separate these two out. But because we have anchor boxes, we can actually capture different shape inside the box. And also, what's a good thing about anchor box is most people, like for YOLO, we predetermine the amount of anchor box we have for each single split region. So now we have is a fixed output. So we will go away. So we basically, remember before I start about object detection, I said that we cannot have a fixed output because of we don't really know how many objects can be in the picture. Now we go all the way back. Now we're gonna have a fixed output again because we predetermined like the amount of thing we have in the image using anchor boxes. It may sound confusing, like sorry, but this is the broad idea of YOLO. So now let's see some examples about YOLO. It's object detection. And I'll paste the link here as well. Same. Like it's impossible to actually share some coding example because everything just like takes really long to train. So sometimes it's best to just find some demo, less error, and this works fine. If you go over here, as you can see, you can choose different model. You can have like 34 megabytes. And of course, this one is the most accurate one, but I like this best. It basically works fast and it's gonna have a bounding box, okay? As you can see, you can wait for a couple of seconds because it does. See, as you can see over here, you can see a person over here. If I put a phone, you can see it as a cell phone. It's pretty cool. But of course, sometimes it doesn't work. For example, if you have a pencil, it says a toothbrush. But you know, it's like, it kind of works, but I don't know why you always classify this as a toothbrush. I guess the pencil does look similar as toothbrush. You can also see as a wallet. It's pretty cool. Yeah, but like, it kind of works. Basically, each one is like an anchor boxes. You split the thing, and that's how YOLO works. So next, so basically, play around with the example a little bit. Also try to change its parameter a little bit, like use another model like YOLO 3, the 256 megabyte one, or the smaller one, and see if there's any difference. You know, it's really fun to just like play around with those AI stuff. So next, since we already finished talking about object detection, object localization, what else can we do about image task? Imagine for a human, we also want to segment the thing out, right? Because for object detection, we do have a bounding box for the object. For example, we like this bounding box have a cat. But what happens if we want pixel to pixel value class? Like we actually want to know where the human is. Like for each, like we have like over here, give an image of this. We actually want to know where the person is. If you like, for example, over here, this is a semantic segmentation. Like this is the person, the pixel to pixel. And if you want instant segmentation, it's actually like every separate person like this. So we want to actually know, besides the bounding box, we want even better accuracy. Like where is it? Like what's the different shape? This is where segmentation comes here. How do we do it? It's actually really relatively simple compared to the RCN Distribution Proposal Network, YOLO. It's basically each pixel will get assigned a class label value. So basically each pixel is going to have a value that says what class is it. It's either a background, for example, a tree, a human. Each pixel will have like that. And basically, and that's how you get semantic segmentation. You basically have, for example, this is the class of person, and other when it's black, it's basically a background. That's we can just put as a black. But for instant segmentation, where we want to basically separate person out, it's similar as we can run a faster RCN or YOLO to get an object, and inside the bounding box, and basically we get each bounding box first as a RCN similar things, and then inside the RCN we basically assign each pixel with a class label value. And I will also show you some example of this. This is also a image segmentation API, like a playground basically. It's pretty fun. You can go to this website. It's similar as a body pixel webcam, but you basically segment the thing out. As you can see over here, you can basically segment my head out, my clothes out, as you can see over here. Pretty cool, huh? Like when they are training the model, they basically assign this. For example, the pixel over here, like this other way I can do. Like as you can see over here, they assign the purple one as a head class. Here is probably some other class, and the white is background class. You can play around with this. You can have like segmentation, like different kind of things you can play around with. Okay. Yeah, so play around with it after the workshop if you want. And yeah, so after we basically understand how it works, so like this is a bonus. So one more problem with the CNN. Do you remember that I say in the beginning, besides the problem with CNN that only output a classification, and sometimes it's not useful because we want more information. Another problem is it only works with a fixed size image. If we train a 50 times 50 image CNN, if you want to use it, we have to basically pre-transform the image we want into the size that actually compatible with CNN. But what if we want to train CNN that actually useful for more broad range of image size? This is where we have to use one new component that just come out recent years called global average pooling. Remember the pooling I said before? I should put these slides before, but like pooling is basically reduce. For example, if this is a feature map, pooling basically reduce the size of feature map. That's it. That's really simple. The max pool is basically you have a 2 times 2 max pool. You basically choose the max pool, or average pooling. You basically just take the average of these 4. And how can we use the pooling to solve the problem of like fixed size? It's called global average pooling. What is global average pooling? Global average pooling is actually just take the whole feature map and just average them. That's it. Remember remember what CNN looks like the model? It's basically feature map, right? We have different feature map and the fully connected layer. Now what we do is instead of basically flatten the feature map out into a fully connected layer, we skip this part. Instead, we just basically use a global average pooling to pull to this only the one times one pixel. Why it works? Why it can work in different size image? Because maybe, for example, we're passing a 100 times the 200 image. Maybe we'll get like in this feature map layer, we're gonna get like a 4 times 4 image. If we use global average pooling, we're gonna get 1 times 1 pixel, right? But if we get a larger image, for example, 500 times 500, we may get like for this layer, we may get like 10 times 10. But if we do the global average pooling again, you will be the same size, become a 3, basically become the same as a 3 times 1 times 3 pixel. So basically now we can increase the image size and it still can run model, because now the global average pooling basically is like scalable. Like you can basically put different image size and you can run to the global average pooling and you return the same size, same predetermined size. All right. And I think this is basically all the topics I want to cover. It's a lot. Like basically I covered the whole convolutional neural network image processing tasks about like deep learning. So it's definitely like reasonable that you don't understand a lot of it, but like I hope if you have time to rewatch the workshop videos. And here's a moral of the story. Deep learning basically involves creativity. In my opinion, as long as we find a good evaluation function, error function, and some way of outputting the stuff we want, we can make artificial intelligence do all kinds of tasks. That's just my understanding. So like, yeah, so I hope you guys learn something from this workshop. And if you're interested, of course, you can look online on Google. They have more resources there and a better explanation. Yeah, thank you very much. And hope you, thanks for coming. I will stay here for a little while. And if you have any question, just feel free to ask me. I will be here. Yeah, thanks for coming. I'll probably post the recording to the UCI workshop online, but I will definitely tell you guys. Yeah, thank you for coming.